for the problem statement, our study focuses on why drivers need to brake earlier when approaching a speed bump during rainy weather compared to the sunny weather. When it rains, the road becomes wet and slippery. This reduces the friction between the tires and the road surface. As a result, the vehicle takes a longer distance to slow down and stop. If drivers brake the same distance as they can do on a dry road, the vehicle may not slow down enough before reaching the speed bump. This can increase the risk of accident and loss of vehicle control. Therefore, we will use the concept of friction, Newton's second law, and linear motion equation to explain why braking earlier is necessary on wet roads.
We'll go through the wastelands, through the highways, and on we'll go.
Why friction force, Newton's second law, and linear motion equation is used? Friction force that opposes motion between tires and road surface. So dry roads equals to higher coefficient of friction, while wet roads is lower coefficient of friction due to water reduces grip. Lower friction, which means vehicle cannot slow down effectively. Therefore, stopping distance become longer on wet roads. Now, why Newton's second law? Newton's second law states F equals to ma. The braking force is provided by friction. On wet roads, friction force decreases, while smaller force means smaller deceleration. The vehicle slows down more slowly. Therefore, longer distance is needed to stop the vehicle. Linear motion equation. Now, the stopping distance calculated using v squared equals to u squared plus 2as. In this case, we are calculating the value of a, which means the acceleration. Wet roads produce smaller deceleration. Therefore, stopping distance increase significantly during rainy conditions.
Okay, now for our experiment procedures. To ensure the fair comparison, we use the same motorcycle, the same rider, the same route, and the same speed bump throughout the experiment. First, we conducted the test on a dry road before it rained. The rider accelerated the motorcycle up to 27 km per hour and began braking at mark point before the speed bump, reducing the speed to 20 km per hour just before reaching the speed bump. The braking distance was measured and recorded, and the test was repeated 5 times. After rainfall, we repeated the same procedure on the same road under naturally wet condition. The motorcycle again started at 70 km per hour and slowed to 20 km per hour before the speed bump. The braking distance was recorded for another 5 trials. And finally, we calculated the average distance for both dry and wet road conditions. This value was then used to calculate the deceleration, braking force, and coefficient of friction for comparison.
So now, before we go to the calculation, I will explain the 3 main concepts that we will use. First, the friction. It is the force that opposes motion between two surfaces in contact. In our case, friction acts between the vehicle tires and the road surface. This friction helps the vehicle slow down when the driver applies the brakes. Second, Newton's second law states that the acceleration of an object depends on the net force acting on it and its mass. In this study, it helps us understand how the braking force affects the vehicle deceleration. A greater braking force causes the vehicle to slow down more quickly. Lastly, the linear motion equation is used to analyze the relationship between velocity, acceleration, and stopping distance. We use this equation to calculate how far a vehicle travels before coming to a complete stop. So these 3 main concepts help us explain why a vehicle requires a longer stopping distance on a wet road compared to the dry road.
Our first calculation is the deceleration of the motorcycle during brake. Deceleration is the rate at which the motorcycle slows down. So we use the formula v squared equals to u squared plus 2as, where u is the initial velocity, v is the final velocity, and a is the deceleration, and s is the braking distance. So first, we converted the speed from 70 km per hour and the 20 km per hour into 19.44 meters per second and 5.56 meters per second. Using the average braking distance of 18 meters for the dry road and 27.9 meters for the wet road, we calculated the deceleration. The results are negative 9.64 meters per second for the dry road and negative 6.22 meters per second for the wet road. The negative sign indicates that the motorcycle is slowing down. Since the dry road has a greater magnitude of deceleration, it shows that the motorcycle can reduce its speed more effectively due to higher friction. Now let's move on to our second calculation, which is calculating the braking force acting on the motorcycle. We applied the Newton's second law, which says F equals to ma. where F is the braking force, M is the combined mass of the motorcycle and rider, which we assume to be 180 kg, and A is the deceleration calculated previously. By substituting the values, we obtain a braking force of 1,735 newtons for the dry road and 1,120 newtons for the wet road. This result shows that the braking force is greater on the dry road because the tires have better grip. On the wet road, the lower friction reduces the braking force, making it more difficult for the motorcycle to slow down within the same distance. The final calculation is the coefficient of friction, represented by the symbol mu. This value indicates the amount of grip between the motorcycle tires and the road surface. We use the formula mu equals to A over G, where A is the deceleration and G is the gravitational acceleration, which is 9.81 meter per second. The calculated coefficient of friction is 0.9 for the dry road and 0.63 for the wet road. The higher coefficient on the dry road means there is a better traction between the tires and the road. In contrast, the lower coefficient on the wet road indicates that it is a reduced friction, which explains why the motorcycle requires a longer distance to reduce its speed safely before hitting the speed bump.
Ethical or value-based reflection. This situation demonstrates how mechanics concept can be applied to improve road safety. By understanding the effects of friction, braking force and distance, drivers can make responsible decisions that protect themselves and others during wet weather conditions. There are 4 value-based reflections that can be used in this concept: responsibility, safety, care for others, and informed decision-making.
Now we are moving on to impact on societies. Braking earlier on wet roads is important to reduce the risk of road accidents, where road surfaces decrease the friction between the tires and the road, causing vehicles to require a longer stopping distance. If drivers do not adjust their braking distance, collisions are more likely to happen. The impact on society includes improved road safety, reduced injuries and fatalities, and lower economic costs related to vehicle damage and medical treatment. Furthermore, increased awareness of braking distance on wet roads can encourage safer driving habits among road users. This contributes to a safer transportation system and enhance the overall well-being of society. Next, we move to conclusion. In conclusion, reducing speed earlier on a wet road before approaching a speed bump is necessary because wet road surfaces provide less friction between the tires and the road. This reduced friction decreases the vehicle ability to decelerate effectively, requiring drivers to begin slowing down earlier compared to driving on dry roads. By reducing speed earlier, drivers can cross speed bumps safely, maintain better vehicle control, and minimize the risk of skidding or losing control, especially during rainy conditions. Okay guys, that's all from us. Thank you. Bye.